Today, I'm going to talk about how we use GPU acceleration for our geodynamic simulation. First, I will introduce our problems. This is the figure of the Earth's surface, and this is the plate tectonics of the Earth's surface movement. The Earth's surface can be decomposed to about 24 plates, and each plate is like a rigid institute, and that can move independently. And because each plate is rigid and they move in different directions, so on the interface of the plates, they produce a strong deformation. And that is where the earthquake happens. And here is showing the strain rate, that is the measurement of the deformation on the different location of the surface. So in the Western Pacific, there is a band of a high strain rate region, that is the high earthquake risk region. So we would like to study how the Earth deforms and how it changes and how it's subject to the plate motion. So one of the example here is showing the Rincon Mountain in Arizona, United States. This region has several north-south mountain range, and in between there's some valleys. And this mountain, they have a different type of rocks. So on the west here, there's a different one type of rock that's made of the shallow volcanic rock. And on the central, there is a more rounded region that is made of the higher temperature. That means that it was deeper in the earth before volcanic rock. And then there's another north-south mountain that's similar to the western mountain. So we can produce a schematic diagram of the topography, like the round part is like here, and the western part and the north part is like this. And these are the blocks that fall from the edge here. And we would like to simulate what kind of process can generate this type of topography. Our equation is Navier-Stokes equation. And this describes how the rock will move with respect to the change of the stress and the gravity. So the most important part is the U is the velocity, and the sigma is the total stress tensors. And in a tectonic environment, the velocity is usually small because the velocity is on the order of the centimeter per year. Or you turn it to SI unit, is about 10 to the minus 9 millimeter per second. So it is similar to how your fingernail grows. So because the velocity is small, so the quadratic turn in velocity can be ignored. So we can ignore this nonlinear velocity turn. Then the problem is the divergence of sigma, this turn, how we relate sigma with respect to the other variable like time, displacement, velocity, and the velocity gradient. And this is called a constitutive equation, or called the rheology of the rock. And this equation is highly nonlinear. So this equation is nonlinear, even though we get rid of this nonlinear term. And there is another simplification that we can do is we can take out this inertial term because the acceleration of the rock is tiny. So if we ignore the acceleration, then the left-hand side is 0. That means now the equation has no time dependence. Now it is a static equation. So these two equations, the Navier-Stokes equation without the nonlinear term and the Stokes equation, these two require different solving techniques. So the Stokes equation, it requires an implicit solver, and it's usually used in a static simulation, like the tectonic process and the mantle convection. And if we use the Navier-Stokes equation, we can use an implicit scheme, and usually it's used for dynamic simulation, like the earthquake rupture or seismic wave propagation. And these two implicit schemes, they have a different advantage and the disadvantages. And for the implicit scheme, the time step size can be quite large because the speed of the considered is in the tectonic speed. So take the typical grid resolution and the tectonic speed, then we can achieve very large time step size. So it's hundreds of thousands of years. And because our target simulation is usually like a million years or even billion years. And the explicit scheme, the speed is elastic wave speed. And the wave speed is on the order of a kilometer per second. So the time step becomes very small. It's on the order of 1 second. So this is a huge change of order of magnitude. But the cost of each time step is different. For the implicit scheme, it requires to solve a large and yield-conditioned linear system. So this is a slow process. For the explicit scheme, it just make matrix vector multiplication. So it's a very fast update. And also, because the system is nonlinear, solving the linear system then means you require another layer of iteration. So usually this type of the iteration is difficult. There is no guarantee to get convergence result. And also the stability of the solver is also a problem. And in explicit scheme, dealing with the nonlinearity is quite easy. So explicit scheme has some advantage, but has a huge disadvantage. So we have some method to deal with the tiny time step. We change the density on the initial term, make it much larger than the true density. And effectively, we slows down the elastic wave. So we slow down that. Now our elastic wave speed is on the order of like 10 to the minus 6 meter per second. So we can now change the time step size from 1 second to 1 year. And this is a numerical non-physical trick. So this trick must be justified by numerical experiments. So we can make the time step size larger and become 1 year. And recently we are trying to make using this explicit scheme and report it on GPU. And we found out that actually explicit scheme has another advantage that is on GPU. And that is the, I will talk about next slide. So for GPU, an explicit algorithm requires solving a sparse matrix inversion. And the sparse matrix inversion on GPU is a tricky problem and it's still quite slow and it's still an ongoing research. And I did some survey and cannot find any suitable library that we can use. So in our geodynamics community, there are several attempts to port our community codes to GPU, but none of them are quite successful. So we use the explicit algorithm, and we only use the dense matrix vector multiplication, and it's quite easy to port the GPU. So our group can obtain 40 times speed up using OpenACC derivatives. So this is the example that I just talked about, and I'm going to show you our numerical simulation. Here we are pulling apart a piece of a rock and generate the deformation is in color. So red is a strong deformation, green is a low deformation. As we pull the two pieces of rock apart, now the fault becomes curved, and the top of the fault becomes a round structure, very similar to what we observed in Arizona. So our strategy was using OpenACC derivative to tell compilers how to accelerate the code with GPU. And we need to add additional derivative to copy the arrays between CPU and the GPU. And these directives, they are ignored by GPU. So we can have a single code base for CPU and the GPU. And our result is that we have two codes. That one is written in Fortran 90. It has like 5,600 lines of code. And we add about 330 lines of OpenACC derivative. And the inventory is between these 300 lines, 140 lines that are used for loop parallelization, like ACC parallel, ACC kernels, and the ACC serial. And the other 120 lines that are used for data copy between CPU and the GPU. So the ACC declare, ACC update, and ACC data. So even though we are using NVIDIA Unified Memory Management, we still need to copy data between CPU and the GPU because these are used in Fortran module. So those are global data. Those are not allocated on the heap. And we will have additional 40 lines used for marking routine. So there's for the ACC routine derivative. And there's another 30 lines for non-trivial data dependency. Those are the ACC atomic or critical. And this last bullet, this type of the non-trivial data dependency is the most difficult part to identify. And we have another code that is the result is we are getting, compared to one CPU, we are getting about 40 times speed up. And also compared to our OpenMP parallelized CPU code, is like 3 times speed up. And we have a second code that is written in C++, and that has this code base is much larger. It has 11,000 lines of the C++. And because the C++ code is more modular, so actually we can achieve the porting on GPU with fewer lines of OpenACC derivatives. And between these 86 lines, there are only 35 lines, so less than half of it is for loop parallelization. And only 3 lines are used for data copy. So because in C++, we don't have to use a global data like our Fortran module. So we don't need to manually copy the data between CPU and the GPU. And there are 30 lines of routine marking and only 15 lines for non-trivial data dependency. And we can achieve similar like 46 times of speed up compared to one single core CPU, or 13 times speed up compared to a 4-core CPU. So our key strategy to port the code to GPU is we have to establish a few benchmarking cases. And these cases are to ensure the GPU code is correct, and also we can measure the power of the speed up. And this benchmarking case should be in small cases, so it can be finished in a few seconds. And we have some script to automatically compare the result of the current code against all the result on CPU. So we can ensure the GPU result is always compatible with the CPU code. We cannot achieve bit-to-bit identical because there are some difference in floating point operation order, but we can get within the machine precision. Also, to get very similar result, we have to fix with the random number seed. We cannot using the time-dependent seeding of the random number. And also, we have to disable fuse, multiply, add instruction on CPU, because on GPU this instruction is still not supported. And we also have a large benchmark case that we use to test the performance. And we also use the OpenACC managed memory mode. And our conclusion is the GPU acceleration is the future for computational geodynamics. And to afford the GPU acceleration, we need to use implicit method. And our code can port it to GPU, and it's 40 times faster than single CPU and 3 times faster than the 16-core CPU. And we found that because our geodynamics code is still under development, it's being changed for different purpose of the research project. So maintaining a single code base for the CPU and the GPU at the same time, very important for us. So doing it with OpenACC is a big advantage. And the last, I would like to thank NVIDIA for this event and also the previous hackathon event. And so we would like to thank its Fortune Lai and the Risk One for their help in the hackathon event. And also thanks for my students, Ches Xu, Ziqing Li, Fang Yi Li, Junyan Chen, Yijun Shen, and Jiqin Chen, and their help in porting the GPU. Thank you.